Okay, good afternoon, good morning, everyone, and welcome to the session Next Generation Showcasing Young Portuguese Talent in Statistics and Data Science, a session that is sponsored by the Portuguese Statistical Society and by CWS, and is organized by me and Wanda Lorenzo, who is also here. So I'm delighted to present our speakers for our session. So the first speaker is Daniela Silva, that is a researcher that is specialized in application in marine ecology. So Daniela, you can start sharing your screen and unmute. Thank you.
Are you seeing my screen?
Yes. Good.
Yes, perfectly. First, starting my presentation, I would like to thank Professor Ligia Rodrigues for inviting me to be here today. It's a great pleasure. So thank you. Today I'm going to present you part of the work that I have been developing since my PhD. And it is focused on the inference of the spatial species distribution by integrating different data sources. So this is the outline of my presentation. I will start introducing the context of the work, then I will make a description of the data and the proposed methods. Next, I will present part of the results, and finally, I will talk just a little bit about the ongoing work. So, given the recent environmental challenges and the need to get sustainable management decisions, it becomes more urgent to seek precise knowledge about biodiversity and species dynamics. And in addition to this concern, the proliferation of high-quality datasets have been introducing a deep complexity to the statistical modeling of biological phenomena. And in the context of this modeling biological phenomena, or species distribution modeling, the spatial and spatial temporal methods have gained prominence. Indeed, the space is essential for modeling the spatial autocorrelation, which can arise from the non-consideration of all important factors that describe the species distribution, while the temporal dynamic is of ecological relevance for the study of the species evolution. And in particular, regarding to the data sources in the scope of fisheries science, there are two main data sources: the fishery-independent data and the fishery-dependent data. The fishery-independent data represents information collected through methods independent from fishing activities. Therefore, the scientific surveys reveal as one of these main data sources, often using standardizing sampling schemes. Indeed, the observed locations are usually selected according to a list of rules. And given the main objective of this campaign, that is monitoring the spatial distribution of the species, the observed locations are sampled over a large spatial region in the sea. And however, these surveys are conducted once or twice a year because they are very expensive, which limits the time series regarding to these data sources. Another usual feature of this data is the high prevalence of zeros resulting from the sampling process. On the other hand, we have the fishery-dependent data that represents information collected directly from fishing activities. One of the big challenges regarding to this data is related to the sampling process. Indeed, the observed locations are usually selected according to the previous knowledge of the fisherman about fish distribution, which results in a stochastic dependence between the point process, which is the sampling location or fishing locations, and the process of interest, which can be represented by biomass index or abundance index. However, this data source has the advantage to generate long time series, because this data source results from commercial activity that is realized every day. However, the spatial coverage is smaller since the fishermen concentrate their efforts in certain regions. So we can conclude that both data sources can bring us information about the fish distributions. They are different, but they are complementary. So this justifies the need for a joint approach for modeling the species distribution. So here we are proposing a new joint model capable to deal with the features of each data source. For instance, the preferential sampling regarding to the fishery dependent data. To illustrate the utility of our approach, we are using the biomass index of sardine at the south coast of Portugal. So to represent fishery independent data or survey data, we are using the biomass index estimated during the PELAG survey in 2017. And to represent fishery-dependent data, we are using the commercial captures for the same area and for the same time of study. Our proposed model is constituted by 5 layers. The 2 first one are focused on the observations. The third layer is focused on modeling the sampling process, and here we distinguish both data sources, and the latent fields are modeled at the 4th layer, and we have finally the parameters at the 5th layer. So given the issue, as I mentioned before, of having a lot of zeros, mainly in survey data or fishery independent data, we proposed a model with a hurdle structure where the process of interest, biomass process, denoted by S, is composed in 2 sub-processes. The first one is the present substance process, denoted by Z. It is a binary variable where 1 indicates species presence and 0 indicates species absence. The second process is the biomass abundance under presence, denoted by Y, and it takes the strictly positive values of the biomass index. Thus, the distribution of the process of interest is given by the product of these 2 independent sub-processes, such that the present substance process is given by a Bernoulli distribution with probability P, and the biomass under presence process is given by a gamma distribution. So this represents the 2 first layers of our model. So we are modeling the probability of presence and the expected value of the biomass process under presence. Here, each linear predictor has a simple form for now, just considering a constant and the latent field with a spatial structure, such that these spatial random effects are modeling according to Gaussian field with matern covariances. However, given the challenges in factorization in dense covariance matrices, we apply an approach based on SPD to approximate the Gaussian field with matern covariance to a Gaussian Markov random field, which is discretely indexed. Now we are moving to the 3rd layer of the model. Here we distinguish both data sources. So we have 2 point processes, one for each data source. The point process representing feature-independent data is denoted by X to the C, and the point process representing feature-dependent data is denoted by X to the C. Regarding to survey data or feature-independent data, the sampling process is independent from the process of interest. So for this process, point process, we are assuming that is homogeneous point process. However, this assumption cannot be made for this commercial data, since there is a stochastic dependence between the point process and the process of interest. So we are assuming that this point process is a homogeneous point process with intensity function lambda, such that the logarithm of this intensity function is given by the linear combination of a constant and the two latent fields that are shared with the two previous linear predictors. These beta parameters represent the degree of preferential sampling associated to each sub-process. In particular, beta prime represents the degree of preferential sampling associated with the presence-absence process, and a larger and positive value of this parameter indicates that fishermen concentrate their efforts in regions with a high presence of the species, while beta parameter quantifies the degree of preferential sampling associated with the biomass process under presence. And this a larger and a positive value of this parameter indicates that fishermen concentrate their efforts in regions with a high amount of fish. Despite this last case being more intuitive, the sampling process motivated by the presence-absence process may make sense in situations where fishermen cannot catch a large amount of fish through fishery restrictions, for instance. Here, this scheme represents, we have a scheme representing the concept behind this model. So we have two latent fields with spatial structure that were independently generated. The first one is used to generate the presence-absence process by using the probability field. The second field is used to generate the expected value of the biomass index under presence. And finally, the process of interest, that is the biomass process, is generated by the product of these two ones. Regarding to the inference of the parameters and the estimation of the process of interest, we used the Laplace approximation of the likelihood of the model. In particular, the distribution of the joint distribution of this model is given by the product of the distribution of the presence-absence process, the biomass process under presence, the distributions of both point process, and the distribution of both latent fields. This property of product was also used to define likelihood, and we finally got the log likelihood of the model that was used to formulate the model in C++. And finally, the model was fitted by using the TMBR package. To evaluate the performance of the model, we conduct a simulation study with 5 scenarios of sampling. These scenarios of sampling range from extremes, where we have that the sampling process is only contingent to one of these sub-processes, Y or Z, to situations where the sampling process is dependent from both processes, the 2, 3, and 4 scenarios. Each scenario was simulated under conditions, the 3 conditions here presented, but and finally to evaluate how the sampling dimensions of both data sources may influence the performance of our model, we consider 4 combinations of sampling dimensions. One where both data sources share identical dimensions. 2 where the commercial data presents a higher dimension, a larger dimension than the fishery, the survey data. And finally, a more occasional situation where the fishery data presents a lower dimension than survey data. To ensure robustness in our study, each scenario and combination of sampling was repeated 100 times. To evaluate the performance of our model, we used these 3 metrics, and to evaluate the contribution of each data sources, we compare 3 models: our proposed model, the fishery-dependent model, that consists of our proposed model, but only using fishery-dependent data or commercial data, and the fishery-independent model that consists of our proposed model without considering the 3rd layer of the model, that is, without modeling the sampling processes, and only using the fishery-independent data or survey data. So, moving on to the results, the model demonstrates the ability to produce unbiased estimates for the beta parameters, which assume great importance in our study. However, there is a slight underestimation for beta in scenarios where it is assumed with a high value. However, in these situations, they are always estimated with significance, which reveals the reliability of our model. Regarding to the prediction performance of our model, there is not much differences between the configurations and scenarios. However, there is a slight improvement with larger data sets. This is the results for the evaluation of contribution of each data source. We can verify that fishery-dependent model and joint models have a high capability to capture the hotspots of the true distribution, possibly due to the strong dependence between the sampling process and the biomass process. And the fishery-independent model produces a better pattern when it uses more data. Regarding to the results for the case study, we verified that the fishery-independent model produces a smooth pattern with some areas indicating presence of the species. The fishery-dependent data, the fishery-independent model produces a well-defined pattern of the biomass index, but finally the joint model can in fact integrate the information of both data sources, which highlights and reveals the ability of our model to highlight the contribution and the impact of each data source. So,
Maria, 30 seconds.
Yeah, I'm just saying one sentence more. Here, now we are working on an extension of this model by integrating temporal components, external coverage, and allowing that the preferentiality degrees may change in time. So I'm done for now. So thank you for your attention. That's all.
Thank you, Daniela, for your talk. It was very interesting. So we let the questions to the end of this session. Okay. So we just to keep on time, the track on time, we are going to pass to our second speaker of this session, that is Maria Almeida Silva. She is an assistant professor at Lusófona University, and she works in the field of stochastic process. So, Maria, you can share your screen.
Can you see?
Yes, perfect. Thank you.
Thank you. Good morning or good afternoon. First of all, I would like to thank you, Portuguese Statistical Society and the CWS for inviting me to present my work on this day. This work is entitled Stratified Sampling of Billing Data and Singular Spectrum Analysis for Smart Meter Installation and Time Series Decomposition in Drinking Water Distribution Systems. This is a joint work with Conceição Amado and Dália Loureiro. In this presentation, I will start with an introduction. Then I will talk about probabilistic stratified sampling based on billing data to select a representative sample of customers. Then I will focus on the composition of flow time series, and in the end, I will present the main conclusions and future work. So the water distribution systems have storage tanks where water is stored, and at the exit they have flow meters measuring the water that exits to a district metered area where the customers receive the water, and these customers, the water that they consume is measured at every month or every 2 months. But there are a technology, the telemetry or smart meters, that allow to obtain the water consumed at a small time interval, for example, 1 hour. Then our goal is to obtain a representative sample of customers where smart meters should be installed such that we can obtain a good inference for the total water consumed in this area, because the smart meter technology is very expensive. But in the literature, usually there are other information needed to select this representative sample of customers, but the Portuguese water utilities doesn't have many information, so we want to do this based only on the billing data. Then we want to use the inferred total water consumed in this area to joined with the water entered in this area and measured by these flow meters to decompose this flow time series into the authorized consumption, but also into unauthorized consumption and real losses that always exist. In the literature, there are several methods to detect bursts, leaks, and unauthorized consumption, but most of them use Excel information. So our goal is to decompose this system input volume into these components without extra information. So how will we do the selection of a representative sample of customers? First, we propose the acquisition of water billing data. This is obtained by the water utility responsible person at the local. And we consider that the best areas is a domestic network zone to do this, since the commercial customers have different behaviors of consumption. Then we need to clean the water billing data, in this case through the elimination of locations without active customers. Then we should do the clustering of the water billing time series. We propose 3 different dissimilarity measures, DTW, pair, and court. And we analyze all of them with hierarchical agglomerative word methods, and we validate it with the Dun, silhouette, and gamma indexes. Then we applied stratified sampling based on strata created in the previous step, and aim to minimize the variance of the error estimator of the total billed consumption. Here we tested the proportional and Neyman allocation. So the case study that we use it to test this methodology is a predominantly domestic water distribution network. Here we have the proportion of each type of consumption of customers. This area has more than 500 locals. Here we can observe the system input volume that was collected between March of 2017 to February of 2019, and the revenue water, that is the billing data collected from April 2017 to March 2019. This month of difference is because of the billing process that is 1 month of delay. Then we computed the non-revenue water with a month times interval for this area. This area has an opportunity to validate this methodology, since all customers have smart meters installed since October 2019. So we can validate our methodology with data after this date. Regarding the results of this methodology, the clustering analysis, the best dissimilarity was the court, and 8 clusters were obtained. 1 cluster has the customers with billed consumption only in summer. 3 clusters have the billed consumption every month, but differing in magnitude. 2 clusters have invoices every 2 months. In this case, one at odd months and the other at even months. Cluster 7 is the only one customer, the firehouse. We can observe here that it's an outlier. And the cluster 8, the final cluster, has the customers without billed water. Here is presented the monthly median consumption of each cluster, and we can observe the difference between all of them. So we applied stratified sampling, and the name and allocation allow it to obtain a lower estimator variance than the proportional allocation, as you can see here. And we decided to that with 53% of the local sampled, we can obtain a good error, in this case, more or less equal to 1%. And this was the proportion that was used for the inference of the total consumption. So we consume, we inferred the water consumption time series. Besides, our approach is to infer the total consumption. We decided that we can apply this for each time instant. So we obtained an estimated water consumption time series, and based on them, we inferred three important informations for water utilities. First of all, the water consumption patterns divided by working day, Saturday and Sunday. And here we can observe these patterns divided by these days. And the solid line is the estimated pattern, and the dashed line is the real, since we have smart meters in all customers, so we can do this comparison. And we can see that the difference is very small. The minimum night consumption is also an important information for water utilities, since in the night is periods of minimum consumption, and they can use this period to estimate leaks. We use this period of time. And estimated the 5% quantile, that is usually a good estimation for the usual consumption at this time. And if the water utilities have more than this, they could have leaks. Compare the estimated and real value we observe that we have a small difference, so this is also a good result. The final inference is the distribution of the volume by the flow that is also used by water utilities to detect leaks. And here also present the estimated and the real distribution of the volume by the flow, and we can also see that they are very similar, which says again that this is a good inference for water utilities. So based on this, now we want to decompose the flow time series into the authorized consumption, unauthorized consumption, and real losses. So for this, we propose to collect the system input flow from the sector. For the same period of time, we need to infer the water consumption over time. In this step, we can use the methodology proposed previously. The third step is the computation of the estimated non-revenue water. This is only the subtraction of the estimated metered water consumption from the system input flow. Then we need to smooth the estimated non-revenue water time series. Why? Because when we represented the real and the estimated non-revenue water, we verified that the variance over time is very different. So we decided we need to smooth the estimated non-revenue water. In this case, the cardinal regression smoother and moving average were used. Then we applied different methods to decompose the smoothed estimated non-revenue water. In this case, Fourier transform, the empirical mode decomposition, the ensemble empirical mode decomposition, the independent component analysis, and singular spectral analysis. Using the same case study, we applied the smoothing to the non-revenue water obtained from the subtraction of the system input volume from the estimated water consumption. And the best smoothed option was the kernel regression smoother with a band equal to 8. And here we can observe the real and smoothed estimated non-revenue water, and now the variance is more similar. Then we applied the decomposition, and in this case, the singular spectral analysis was the best method. The window length was equal to the length of time series plus 1 divided by 2, and number of eigenvalues equal to 50. Here is the representation of this decomposition, and 3 components were obtained plus the residuals. Component 1 and 2 could represent the real losses, the usual leaks. Component 3, the apparent losses and unauthorized consumption. The residuals could be the peak bursts in the real losses category. So, in terms of conclusions, in this work, stochastic methods were used to improve the water loss control in drinking water systems. First, a probabilistic stratified sampling methodology was applied using clustering analysis of billing data to select a representative sample of customers where the smart meters should be installed. And based on these customers, we can infer important information for water loss management with small errors. Then we proposed a methodology based on smoothing time series and singular spectral analysis for the decomposition of flow time series. In terms of future work, we consider that methods of sampling using directly the billing time series could be analyzed to solve the problem of the variability of the estimated authorized metered consumption. Also, the decomposition of flow time series need validation, maybe incorporating filed work. Moreover, a more automatic choice of which component should be grouped needs to be studied, since this identification to obtain the final components is not easy for water utilities since they don't have the knowledge for this choice. This work, the first part of the certified sampling analysis for smart meter installation is already published. I have here the paper. Second part is the submission process. So thank you very much for your attention. I have here my email if you have any questions or want to contact me about the work. Thank you very much.
Oh, thank you, Maria, for your interesting talk, very important about management of water resources. So we are going to put all the questions to the end of the session. So I will go to our third speaker of this session, that is Vanessa Silva. She's an assistant professor at the University of Porto, and she works in the field of multivariate time series. So Vanessa, you can share your screen.
Okay, you can see my...
Yes, perfectly.
Thank you for the nice introduction. Good morning. And first, thank you very much for the invitation, and thank you for being able to broadcast this talk here today. So in this presentation, I will present a methodology for analyzing multivariate multivariate time series data using multi-layer graph structures. Starting with a brief motivation, as you know, new data sources and data gathering devices have increased the complexity and the size of available data sets, especially time series data. In fact, time series data are found everywhere and are a special type of data because they are indexed by time and observations are ordered and correlated. In fact, we can deal with a single time series, which we call univariate time series, or we can deal with two time series, which can be temporally correlated with each other, or in fact, we can deal with thousands of time series, which we call multivariate time series data. Multivariate time series analysis is not trivial due to the challenges posed by serial and cross dependencies, as well as the high dimensionality of the data. And questions like how to plot so many time series or how to summarize these time series are relevant questions and emphasize the importance of developing effective methodologies to deal with this special type of data. Time series analysis via network science arise from this need and offer alternative approach to representing and analyzing time series data. This involves mapping the time series data into network structures where features that summarize time series can be obtained by leveraging the network science methodologies and graph theory. And in this work, I present two new mapping methods for multivariate time series in particular, and a framework for extracting summary topological features from the data. Before that, I briefly present some concepts. In a simple way, a complex network is a graph structures formed by a set of nodes and a set of edges where nodes represent entities or objects of a system, and edges represent connections between the entities of the system. These mathematical structures is widely used to represent different real-life systems. And typically, graphs are represented mathematically by adjacency matrices that are used to analyze and extract measures from the networks using a variety of statistical and network science methods. Okay, another structure is the multi-layer network, that is a high-dimensional graph which represent different systems with different types of connections between the nodes. In these particular structures, each system or subsystem is represented by a graph in an individual layer, and interlayer edges represent connections within the subsystem, and interlayer edges represent connections between different subsystems. Also, a multilayer network can be represented mathematically by a super-adjacency matrix, where the diagonal blocks contain the interlayer connections, and the off-diagonal blocks represent the interlayer connections. These metrics also allow to apply the usual statistical and graph theory methods for these high-dimensional structures, and allows to select different substructures, graphs, by selecting specific connections of this walled multi-layer graph, such as an interlayer graph by selecting only interlayer connections or relations, the interlayer graphs by selecting only the interlayer connections, and all-layer graphs by selecting both type of connections in the multi-layer graph. Okay, based on the powerful structures of multi-layer networks, we developed two new multivariate time series mapping algorithms to transform multivariate time series data into multi-layer networks. We have the multi-layer horizontal visibility graph and the multi-layer quantile graph. These mappings were designed to map the serial correlations within each individual time series data and the lagged cross correlation between different time series data. And the first one is based on the visibility criteria and consists of three main steps. Okay. First, for a multivariate time series data, each time series is mapped on a layer graph using a horizontal visibility graph algorithm. Here, each timestamp is mapped to an individual node in temporal order in the layer graph, and interlayer edges represent horizontal visibility lines between corresponding observations that meet the geometrical condition in the specific time series data. Next, we rescale all the time series components using the min-max scaling to be on the same scale. And for each pairwise time series, we find the time series that represent the maximum of the two time series represented here by the black dashed line. And then we check the cross-horizontal visibility, the visibility, that is a new concept here. We check the cross-horizontal visibility between pairwise of time series components of the time series data, where two arbitrary timestamps, one for each time series, have cross-horizontal visibility if there is a horizontal visibility line between the observations that is not intercepted by any middle observation corresponding to the maximum of the two time series that is in check. That meet the geometrical condition of the two time series. In this picture, we represent the time series values by corresponding color bars, and cross-horizontal visibility is represented between the data points, is represented here by bicolor lines that connect the corresponding timestamps. Okay, finally, we add interlayer edges to our multi-layer network between each pairwise time series and corresponding pairwise layer graphs using the cross-horizontal visibility checks of the before steps, and the resulting multi-layer horizontal visibility graph is shown in these pictures, where solid lines represent the interlayer visibility connections, and the dashed lines represent the interlayer edges that represent the cross-horizontal visibility connections between pairwise of time series components. Okay, the second mapping is the multi-layer quantile graph algorithms that aims to map a multivariate time series into a smaller or reduced multi-layer network structure. It is based on a probability transition concept and consists in the next three main steps. Again, first, we need map each individual time series to a layer graph. Here, we use the quantile graph algorithm, dividing the time series support into appropriate number of sample quantiles. Each sample quantile is represented by an individual node in the corresponding graph layer, and intralayer edges are established based on the transition between successive quantiles. For example, in this year, there are two successive transitions from the second quantile to the fourth quantile in the first time series. So we have a directed and weighted edge representing this probability transition in the first layer graph between the nodes, the node 2 for the node 4. Okay, in the second step, we connect the contemporaneous quantiles, that is, the quantiles in the same corresponding to the same timestamps between pairwise time series, again, using the corresponding quantile sequences obtained in the first step. Finally, we obtain the multi-layer quantile graph, establishing the interlayer edges based on these pairwise contemporaneous quantiles. And these interlayer edges here are bidirectional and weighted, with the weights of the edge represent the transition probability of contemporaneous quantiles. Note that this network is a more reduced representation of the multivariate time series data and the multi-layer network in comparison comparing to the multi-layer horizontal visibility graph, for example, as we have a reduced number of the sample quantiles in this mapping method. Okay. In the network science, networks are characterized and summarized by topological features, such as features related to node centrality, graph distance, clusterings, and communities in the networks. And these features are a fingerprint of the time series data, the network data, and can characterize different networks and different systems and different data. The idea behind of this work aims to use topological features to enrich the set of multivariate time series features. Thus, we propose novel features based on multi-layer networks and its substructures, subgraph structures, and we use them to study and analyze multivariate time series data. We can have intralayer features that are related to intralayer edges and with serial dependency of the data. We can have interlayer features related with interlayer edges and with cross dependency of pairwise time series, and all layer and relational features which are related with both intralayer and interlayer connections, and also with similarity between the pairwise layers. That means with the pairwise time series data. Okay, We propose a method that we named MNetF method, which represents a feature vector that summarizes a multivariate time series. It is formed by a concatenation of different topological features that are extracted from the two multi-layer network and their different subgraphs, interlayer, interlayer, and all-layer graphs that result from the multi-layer horizontal visibility graph and multi-layer quantile graph mapping methods from the original multivariate time series. Okay. In this slide, this diagram represents overall this feature extraction process, and it is illustrated the framework that will be available soon and that incorporate the mapping methods and feature extraction process presented in this talk. In summary, this framework takes a multivariate time series as input or a set of multivariate time series data as input and map it to multi-layer networks, multi-layer horizontal visibility graph and multi-layer quantile graph, and extract topological features from the resulting networks. The resulting output features can then be used to different time series mining tasks from clustering, classification, anomaly detection, forecasting also, and others. Okay, to show some examples of the use of this framework. In this case, to show an example of exploratory analysis of multivariate time series features, we here are presented different bivariate time series related using different statistical models, well known. We generating several samples of these models. Each represent different data characteristics with different properties regarding to serial and cross-dependency of the data. And I mapped each multivariate time series data into a multi-layer horizontal visibility graph and multi-layer quantile graph. And we extract the corresponding topological features using the MNetF method. For example, here we have the degree distribution of the multi-layer horizontal visibility graph in particular for the data. For each sample of the data, the degree distribution measures the fraction of nodes in the graph with a given number of the edges. This is important measures in network science to characterize different different types of networks, for example, and we can analyze that the resulting distribution curves are related with specific properties of the models and the resulting different types of the distribution extracted from the different subgraphs of the multi-layer network seems to relate with the specific correlations of the time series models also. Okay, here is presented the principal component analysis plot resulting from the multi-layer network features. We can identify some well-formed clusters that correspond to the most different models. All topological features contribute to the arrangement of samples, which capture different properties of time series models. We can identify and relate specific topological measures with specific properties of the data. The different mapping methods also produce different results because it is different mapping concepts, and these indicate that they capture different properties of the data. Okay, now here we have another application example for proposed methodology in this case classification of multivariate time series data. For this, we use 18 multivariate time series datasets available in the classification benchmark dataset repository, very popular in the fields. The time series have different types of the data, different lengths, different numbers of dimensions, different numbers of classes. And for this task, we use a random forest ensemble learning method, and we do several experiments, okay? And in this simple table, we present the general summary of the results obtained for the 18 datasets using the set of features extracted from the multilayer horizontal visibility graph and multilayer quantile graph of the data. We can conclude that results are overall similar for both mappings, and the better results are obtained using the visibility mapping, as you can see in the tailored table of the results. Here we can see the different time series datasets. We have the different types, different characteristics and properties, and we can see that the overall multilayer horizontal visibility graph can obtain the better results, but for multilayer quantile graph features, the results are very similar, okay? But these different mapping methods can capture different properties of the data, and overall, the results, in general, we consider these results to very good and promising for this work. Given the global nature of the topological features that are very global over the multi-layer networks, and also we did not use more advanced techniques of feature engineering, for example, selecting and filtering more representative features that could improve the results probably. But this is not proposed in this work. Okay, to conclude, I conclude that multi-layer networks and network science can be a powerful tool for multivariate time series mining problems. In fact, this is an alternative approach, not a better approach, of course, but can be alternative and a complementary approach to analyze this specific and complex type of data that is the multivariate time series data. Furthermore, these applications have several possible paths yet to be explored, okay, and to improve. Examples include improve the presented framework, for example, considering advanced feature engineering methods in the case of extracting more representative features for the data. Another example is adapt multivariate multi-layer mapping methods to spatial temporal data models, for example, and a recent work we have going is to use mapping time series mapping algorithms to privacy preserving time series data, for example. And okay, I finish. Thank you very much for your attention. This work also have been made with my professors, Maria Eduarda Silva, Pedro Ribeiro, and Fernando Silva. Thank you.
Thank you, Vanessa, for your interesting talk. I think we have time for one question. I don't know if there is any question on the chat or on the Q&A. Let me see if someone wants to talk. If not, I will finish, and I would like to thank on behalf of the Portuguese Statistical Society and CWS. I'd like to thank Daniela, Maria Almeida, and Vanessa for your insightful contributions and for sharing your expertise during this session. And I wish you all a happy International Day of Women in Statistics and Data Science 2024. And thank you.